So we're going to start out with the SN2 and look at all the basic pieces behind this. We're going to do a similar walkthrough for the SN1 in the next video. What I would like you to do is watch this video all the way through and really kind of absorb and process as much of it as you can, and then try and apply it to an SN1 reaction without watching the SN1 video. Okay, that would be my ideal scenario. And then move to the SN1 and make those comparisons to see if you're making all the proper connections. Okay, so to go ahead and start, we do have a lot of colors in here, and I'm going to attempt to kind of code those as we go and explain things. Okay, so first off, in blue, we've got what I'm going to call the substrate. That blue is a bit undercoated because the substrate blue should actually be covering this entire piece. The substrate is referencing everything that we're starting with, including the leaving group, our carbon structure, okay? Which might be a bit of an overstatement, but it's the place where the leaving group is located, okay? It is what is being acted upon, okay? And we'll clarify that in a second. So this is being acted upon. In red, okay, we have what is referenced as or shown as a nuke, which is actually referencing a nucleophile. Okay, the nucleophile is the electron donor. Okay, it is what is doing the acting, if you will. Okay, which should help us out because what is it doing the acting on? It's doing the acting on the substrate. So if the nucleophile was an electron donor, the substrate must be an electron acceptor. And because it is an electron acceptor, we also know then that the substrate could also equally be labeled as an electrophile because it needs to be accepting electrons from the nucleophile. Okay. Next pieces we've got that Lg up there. That Lg is standing for leaving group. Okay. It's kind of weird to label the leaving group because it's connected to the substrate in the reactant, and then in the product side it's not connected anymore. Okay, so that's where it's easier to see what the leaving group was, is because it's fully disconnected. The leaving group steals electrons or takes electrons from our substrate. Okay. And that's going to be helpful, and in fact we can color code that, takes electrons from the substrate. Okay, that phrasing helps us to think about what kind of curved arrows we should be using to describe this. And then the last thing that we see color coded in there is our solvent. Okay, the solvent is typically shown under the arrow, but you have to be careful because sometimes the solvent can be the nucleophile, so be careful with that. So the solvent's role is important. Sometimes it's shown, and sometimes it's not. Okay, you just kind of have to roll with it to come up with those predictions on why and when it would be relevant. Okay, typically you're looking at something that's in there in a vast concentration, okay, or a large concentration. That becomes a bit of a weak statement to make because there's no concentration specified in our reaction. Okay, so it's kind of hard to tell that out. Okay, the solvent is usually playing a minor role to the overall reaction, but it does have some effects, and it can allow us to predict which mechanism we end up running instead of others. So it is important to acknowledge its presence. It is important to evaluate it and be able to classify it according to those classifications we talked back about in Unit 1. Okay, protic, polar aprotic, and just straight up nonpolar. So as we address them in Unit 1, we needed to be able to find those classifications. Why? We'll see why, because those classifications are going to help us to acknowledge what would be a good solvent or not as a reaction runs. Okay? So those are our four primary classifications for our reaction. We're calling this an SN2, okay, which was our 2 type or 2 of our 1, which meant two of our possible mechanisms we can come up with, which was listed as a simultaneous. Okay, this was breaking the bond simultaneous to the formation of the nucleophile bond. Okay, so with that wording, we should be able to draw some now curved arrows with this. Okay, and I'm going to have to be careful here because we've got all sorts of stuff hidden underneath this. Okay, so one thing that we can draw attention to, okay, so that I won't erase, I'm going to erase the substrate and I'm going to erase the solvent for the moment, because the nucleophile and the leaving group definitions have some useful stuff for us. First and foremost, the leaving group needs to steal electrons from the substrate. To do that, we're going to have to take electrons in the bond that connects the leaving group to the substrate, that's that black bond, and show those electrons go towards the leaving group. What we've now done by adding that arrow is defined or followed the rule of what a leaving group is. So if we know that definition, that can help us decide how the arrows move. The next one is our nucleophile was an electron donor. So it needs to be sharing electrons. So we will take that negatively charged nucleophile and we will show those electrons being shared with our substrate. Okay. What is the result of this? Well, what happens to the bond that was connecting the leaving group to our structure? Well, that bond is now no longer present. Okay, we've gotten rid of it. And that's why our leaving group is floating off way to the side. We could just have easily shown the leaving group right next to it. Okay, and that would have been fair, except that can get confusing. Okay, and this becomes one of the weird things in OChem. In OChem, what we're talking about is only moving electrons. Our drawings make it look like molecules have moved to different locations. That's only done as a clarification to allow us to separate those molecules away from each other and allow us to see them a little bit better. But ultimately, it's only the electrons that have moved. Okay? This is all happening in a single step. Okay? We are going from reactant to product, one smooth simultaneous step. Okay? So if we bring in the information that we talked about before with our rates, okay, the rate is going to be dependent on our slow step because there's only one step. Okay, it by definition is going to involve the reactants of that slow step. Okay, and here are our reactants. We have the substrate and the nucleophile. For those people saying, well, how do we figure out the orders for those? You're right. Those orders need to be solved experimentally. This is one of the beauties in OChem, though. They need to be solved experimentally for a reaction. For a mechanistic step, the order is the coefficient on the reagent. And you might say, well, I haven't seen coefficients on any of the reagents. What's the coefficient, the number in front for these? It's 1. That's why we didn't show it. Okay? We can cheat and avoid having to specify that because it is by definition 1. What we're showing in mechanistic steps is just the number of those particles, which means the orders for those reagents in our rate law will be 1, okay, which is cool. Okay, we now have those rates. Now that we have a rate law, we can actually move to the next big aspect of this. I can look at the order for the overall reaction. That means I sum the orders for the individual reagents and I would get a second order reaction. Okay, if it is a second order reaction, I could call it bimolecular. Why do we call it SN2? Because there are two things in the rate law. Why do we call it bimolecular? Because that's the English language to explain the rate law. That's where the 2 is coming from. Okay, this is easily confused with the number of steps. Okay, they mean different things. Don't reference it based off of the number of steps. Okay, so we now have our rate law for this reaction. We know it is bimolecular. We know it's all happening at once. Okay, and so we've got a mechanism, we've got a rate law, everything's good within the world. Okay, so are there other things that we could try and pull from this? Okay, so for instance, what about the solvent? Or sorry, I don't want to say solvent. What about our nucleophile? Okay, what could we describe about it? Well, it is currently negative. Did it have to be negative? Okay, what happens if I make that less negative? What if it's not negative, it's now neutral? Okay, and we can just delete the sodium. Well, now it is less likely to share those electrons, which means the effective concentration for the nucleophile decreases. Well, if the nucleophile concentration decreases, the rate decreases. Okay? Which means we'd have a slower reaction. So that wouldn't be good for an SN2. For an SN2, I want this to happen as fast as humanly possible, because I want to get out of class faster, and I want my nucleophile to be as high a concentration as humanly possible. Okay? Within our rate, what we're talking about is not just concentration, but activity. How reactive is it? So the more negative that nucleophile becomes, the better our reaction. Okay, so this means the nucleophile should be negative. Well, negative gets a bit vague. We aren't really saying it should be negative. We just want it to be more active. Okay, which person would be able to be more active? Yeah, let's not go that direction. We're just going to jump to wording I want to use. We're going to call it strong. Okay, I want a strong nucleophile. Okay, negative tends to be a big red flag for a strong nucleophile because it has lots of electrons, and because nucleophiles donate electrons, that makes sense. Okay, so the nucleophile for an SN2 should be strong, i.e. negative. Okay, leaving group, because we already addressed that, or started to address that. Let's look at it. What do I want for the leaving group? Well, I want it to leave. And for those people wondering about the odd pause and silence there, that's about it. It needs to be a good leaving group. Okay? What would make it a good leaving group? That would be an awesome topic for a video on leaving groups. You should go reference that video. Okay? So look through the YouTube channel for the leaving group video, or if you're in my class, go to the Canvas modules and look for the leaving group video there. I'll try and see if I can embed a link to it in the YouTube video. Okay, so we need a good leaving group. So that's now off the table. So now let's take a look at our substrate. Okay, well, the substrate is our carbon structure. What could we change about our carbon structure? Okay, well, what kind of carbon structure do we currently have? So let's redraw it over here. We had our leaving group. We go, well, that's not particularly exciting as far as a carbon structure, so let's go through and add some more detail behind it. So we could add in all the implied atoms. Okay, do I care about this carbon? No. Why should I not care about that carbon and all those hydrogens? Okay, the chemistry is happening at that other carbon. Okay, it is happening at our substrate carbon where the leaving group is connected. Those red carbons and hydrogens, or the red circled ones, are too far away to have any effect. So I can effectively ignore those. Okay, where should I care? I'm going to want to care as close as humanly possible to that blue dot, which means the carbon here, the hydrogen here, and then theoretically also the leaving group. But the leaving group we've already addressed. So what could you describe about that blue dot of a carbon? I know that's vague, but see what you can come up with. As a hint, it is connected to only one other carbon. This would be a primary carbon. Okay? Or in this case, if that leaving group was a halide, it would be a primary halide, because the leaving group is connected to a carbon that is only connected to one other carbon. Could I theoretically change this to now, instead of being a hydrogen there, I now have a carbon? Well, now it would be secondary. And I could also change it to be another carbon So it would now be tertiary. How does that affect this reaction? Okay. Well, again, it's going to come back to what are the differences between these. So if we throw on our hydrogens for the other position, okay, how does that affect our reaction if we switch from carbon or from hydrogen as shown in our original mechanism to now carbons? Well, what is the difference between carbon and hydrogen? As we discussed when we looked at ion stabilities, carbon has more electrons than hydrogen. If I put more electrons around that blue carbon, what does that do or change about the likelihood of a nucleophile wanting to come in, and react with it? That's going to decrease the likelihood of it actually happening, which means if I'm going to do an SN2 reaction, I would affect or expect the primary substrate to react faster than the secondary, faster than the tertiary. Well, why? Because the tertiary contributes a bunch of electron junk. Okay? That electron junk gets more scientifically referenced as steric hindrance. Okay? So we now have this new term coming up of steric hindrance. And steric hindrance is a big deal. Okay? So we can think about steric hindrance as just electron junk. There's electron junk, we've got steric hindrance. So when I run an SN2 reaction, I want to minimize that steric hindrance as much as possible. Okay? Which is going to pop up again here in a second, because what we're talking about as we bring in the substrate is where that nucleophile reacts. So let's look at the arrows that we showed for that nucleophile. It shows the electrons coming in from the backside of that leaving group. Why do I not have the arrow go all the way over there? For those of you being, well, that just looks like a stupid arrow. Do better than that. Okay. What is the leaving group leaving with? Electrons. What is the nucleophile bringing in? Electrons. What happens if electrons get near electrons? They repel. Since the leaving group was there first, if the nucleophile tried to come in, the leaving group would chase it away, preventing that connection, which means the nucleophile has to come in from the backside of that leaving group bond, making it all the more important what atoms are connected to our reactive carbon. Okay? So what we could go through and do, and I have a feeling it's going to be right in the middle of our steric hindrance, is we could look at the transition state. Yep, so I'm going to end up having to erase all of that. Oh, awesome. Yeah. We could look at a transition state. How do we know we're talking about a transition state? Because we got the brackets and we see a double dagger. The nucleophile is coming in trying to make a bond with our carbon at the exact same instant as the leaving group is trying to leave. Okay? And it has to come in from the backside, because if the nucleophile came in from the top side, it's going to butt up against the leaving group. Okay? The other argument that is much more valid, which we talked about back in molecular orbital theory, is that if we look at the carbon leaving group bond, the molecular bonding orbital, where there are electrons, okay, we have electrons here. The anti-bonding orbital, where our nuclei are these black dots, the anti-bonding orbital looks something along these lines. Why is that important? The anti-bonding orbital has no electrons in it. Where can the nucleophile dump electrons? It would have to dump them into an orbital that it could overlap with. That overlapping orbital happens to be on the direct opposite side of our bond with the leaving group. That's why it's coming in from the backside of that leaving group bond. It's a molecular orbital argument for why this works this way. not just hand wavy will electrons get in the way. It's literally, that's the only place that we can place electrons, is on the backside of that bond. Okay, so that's why we talk about molecular orbital theory. I'll shut up about molecular orbitals now, and we can go back to just our hand wavy arguments. The nucleophile comes in, the leaving group leaves, and we get our transition state. Okay, so cool. If we had this primary structure, everything works out nicely. We get this steric hindrance aspect that we need to be concerned about. Okay, when we talk about the reaction itself, it's happening as a backside. Okay, or the reaction is happening on the backside of the leaving group bond. Okay, so we could reference this as a backside attack. Okay, so cool. We've addressed the nucleophile, the leaving group, the substrate. Before we get into the solvent, let's push this just a little bit further. Let's say, just for giggles, instead of it being primary, let's make it secondary. And let's make it secondary where one of those hydrogens is just a CH3. Okay, so if we go through and we look at our other drawing down there, there's our CH3. We would then have to draw on our CH3 in our product, and right, we would just have our answer and be like, well, that's not a big deal, Mike. Why are we talking about that? We'll take a closer look, and I'm going to suggest that you take a closer look at the product, because that one's the least busy of all of them. Is there anything kind of important popping up in the product that you should be concerned about? Here's your hint. Some more hints. That is a chiral atom. Okay, why is that important? Well, if there's a chiral atom there was a chiral atom all the way back at our starting material. Okay, why does that become important? Okay, well, let's clean some of this up, and let's make that chiral atom a little bit more apparent. Let's show a wedge for our CH3 and an H being dashed. Okay, when our reaction goes through and happens, our nucleophile comes in from the backside, kicking out our hydrogen. And if we drew out our result for our potential product, we would show this being wedged as our CH3 and our hydrogen being here. Yeah? I still don't see why this is relevant. Okay? Hopefully it'll sink in here in a little bit. Typically, when we're running these reactions, the leaving group is a halogen. Halogens have very high atomic mass, which means they are probably going to be assigned a 1 when it comes to R and S. We have that chain, 3, 4. If we draw this out, 1 to 2, 2 to 3, 3 to 4, that is now going, and because our hydrogen's aimed away from us, that directionality is counterclockwise. That I would assign as S. Our nucleophile is usually coming in as a heteroatom. Most heteroatoms have higher atomic masses than carbon. So in our product, our nucleophile would be 1. Our CH2 is still 2. 3, 4. Our hydrogen is aimed away from us. We're now aimed to 3 clockwise R. Our stereochemistry just changed. Yes. This becomes the problem or a complication with an SN2. In our SN2, because of the dynamics of how that mechanism occurs, we are forced to invert our stereochemistry. And it all comes back to that backside attack. As a complication, we invert stereochemistry. Okay? It is not a guarantee. It is typically inversion of stereochemistry. What do I mean by typically? Probably 80% of the time it's an inversion of stereochemistry. Okay? And that's actually probably a lie. It's probably closer to 90% of the time it's an inversion of stereochemistry. The only case where it isn't an inversion is when your nucleophile has a different priority than your leaving group. Okay? And that tends to be rare, but it can happen. So if we're running a reaction that we think is an SN2, we need to address stereochemistry if it is present. For instance, the primary reaction we ran, the primary substrate, we didn't have to worry about it. But as soon as it became secondary, we did have to worry about it. Okay? So what we could do is flag our secondary substrate as a potential inversion of stereochemistry. Okay? Whew, that's a whole lot of stuff. I hope that would be done with it, except we also have the solvent that we have to address in this. Okay? So let's think about the solvent. In our solvent characteristics, the role of a solvent is to dissolve. Okay, we're trying to get a homogeneous system, pulling out some old school fundamental chemistry terms. If we think through what we've got as reactants, so I'm going to have to clear away that reactant stuff again. In our reactants, we have this organic, largely non-polar starting material in our substrate. Okay, and then we also have our nucleophile, which to be strong is probably ionic, which means we're probably looking at something as ionic. So what we want to dissolve this is something that can dissolve both of those. So if we write out our classifications for our solvents, we have protic, we have polar, aprotic, and we have nonpolar. Well, the nonpolar probably won't do a good job of dissolving the ionic. So because of that, we'll cross out the nonpolar solvent because it won't dissolve the ionic solvent. The protic solvent, similarly, probably won't dissolve the nonpolar, so we could cross that one out. It doesn't satisfy the minimums of our system, which really only leaves one choice. We would need to have a polar aprotic solvent to get both of these things into the same phase. And sure enough, when we're looking at an SN2 reaction, the ideal solvent is a polar aprotic solvent. Okay? That was a lot of material to throw at you. But what we tried to do was systematically walk through what we established as our mechanism, draw out our mechanism, and then look at each of the individual repercussions that could come out of establishing that as our mechanism. Okay? That is a challenge and no small feat. But what we just addressed right here is pretty much everything to do with SN2 without looking at any real detailed examples. Okay? So when you look at a reaction, you should be able to try and identify each of these characteristics as we moved through it, okay, to be able to classify. We haven't whittled down some of the rules, so don't stress too much, but this is what I want you to be able to go through and do for the SN1 mechanism. Okay? Lots of detail out here, so what I'm going to go ahead and do is clear it all away in 3, 2, 1. What we're going to see is the SN1 in the next video. In that next video for our SN1, I want you to open it, or first open it up, look at that initial slide that starts it off, and I want you to generate everything we just generated for the SN2, but I want you to do it for the SN1. Okay? Do as much of that as you can. We'll make the SN1 video very shorter, because I'll try to not actually talk through it, and I'll just try and show most of those pieces as opposed to looking at each of the individual steps. Okay. With that, if you've made it through this, excellent job. This was a beast of a half an hour.